Hello everyone. Today, we're diving into how we can recover the function phi of n using Möbius inversion. Let's explore this fascinating topic together. Last time we proved that if you add phi of d over all divisors of n, the total comes out to n.
I remember that. We grouped numbers from 1 to n by their greatest common divisor with n to get that formula.
Here is that divisor-sum identity written as a compact equation. It will serve as our starting point.
Right now, the equation hides phi inside a sum over divisors. I want a way to solve it and get phi of n by itself.
Conceptually, take the numbers from 1 up to n and sort them into piles according to their greatest common divisor with n. For any fixed divisor d of n, we showed there are exactly phi of n divided by d numbers whose greatest common divisor with n equals that d.
So if we add up the sizes of all these piles, we must get back n, because every number from 1 to n is in exactly one pile.
Our challenge now is to run this reasoning in reverse. Starting from the divisor-sum identity, use Möbius inversion to peel phi of n out of the sum. To pull phi of n out of that divisor-sum, we switch to the language of arithmetic functions and Dirichlet convolution.
So we treat phi, the constant one function, and the identity function as objects we can multiply using convolution, right?
This equation says that phi convolved with the constant one function gives the identity function sending n to n.
So the divisor sum we started with is exactly the statement that phi star 1 equals the identity function.
We have four key players: phi, the constant one function, the Möbius function mu, and the identity function that sends n to n. All are functions on the positive integers. The original divisor sum is just another way of saying that phi convolved with the constant one function gives the identity function. Möbius inversion tells us that convolving with mu is the inverse operation to convolving with the constant one function.
So if convolving with mu undoes convolving with the constant one function, then starting from the identity function we can convolve with mu to get phi back.
Here is the concrete result. Phi of n equals the sum over all divisors d of n of mu of d times n over d.
Nice! This gives an explicit recipe for computing phi of n just by knowing mu for its divisors.
Let us see the new formula in action by computing phi of 12.
I know phi of 12 should count numbers up to 12 that are coprime to 12, but this time we will use the Möbius formula instead of direct counting.
First, list the positive divisors of 12, which are 1, 2, 3, 4, 6, and 12. Next, recall the Möbius mu values for those divisors, using their prime factorizations to decide whether mu is 1, -1, or 0.
With divisors and mu values ready, we can plug everything into the divisor sum for phi of 12.
This calculation shows the sum over divisors explicitly, then substitutes the numerical mu values and simplifies to get 4.
That matches the usual count of numbers less than or equal to 12 that are coprime to 12, so the formula checks out.
Before we finish, let us step back and see the overall strategy we used to uncover a formula for phi of n.
It felt like we transformed a messy sum into a clean formula by changing the point of view.
We began with a combinatorial identity that relates phi values on divisors of n to n itself. Then we rephrased that identity using the convolution operation on arithmetic functions, which packaged the divisor sum neatly.
Once it was written in convolution language, we could apply Möbius inversion as an algebraic inverse step.
That inverse step produced a divisor sum where phi of n is expressed explicitly in terms of mu and the quotients n over its divisors. This final equation is the key takeaway. It is often easier to understand an arithmetic function by relating it to a simpler one and then inverting using Möbius. Let us close with one quick practice question and a short reflection. Your task is to use the Möbius formula to compute phi of 18, summing mu of d times 18 over d across all divisors d of 18.
So I should list the divisors of 18, find mu for each one, multiply by 18 over that divisor, and then add everything up.
Working it out, the divisors are 1, 2, 3, 6, 9, and 18, and their mu values are 1, minus 1, minus 1, 1, 0, and 0. Multiplying each mu value by the corresponding quotient 18 over d and adding gives 18 minus 9 minus 6 plus 3, which simplifies to 6. So 5/18 equals 6.
That matches the 6 numbers up to 18 that are coprime to 18, so the method checks out again. To me, this Möbius formula feels especially natural when the function is already defined by a divisor sum, like the way phi came from counting residues in each GCD class.
Exactly. Möbius inversion shines whenever your information is bundled into sums over divisors, while the product formula is better when you already know the prime factorization of n. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.